Okay, in this video we're going to continue on with number systems. Last time we learned how to convert to decimal from most Arabic style number systems. Now we're going to learn how to convert from decimal. And if we know these two strategies, pretty much any number system we can convert to decimal, and then from decimal we can convert it to any other number system. Okay, so these are the tricks that we're going to use here. All right, so just like last time, we're going to go ahead and convert decimal to decimal using this system. It doesn't sound very useful, but it gives us a relatable way to apply this to other number systems. All right, so again, decimal to decimal, not really accomplishing anything, but it shows us the methodology we're going to use for other number systems. So start with the example 2,781. Now this is the value as a decimal, right? So we print out our number, we write it down here, and we've got some goal, right? We don't know how many digits necessarily it's going to be, but we've got a few digits lined up here. So the first step is we divide by the base and place the remainder in the rightmost place. Okay, so if here we're dividing by 10, right? That's our base. So divide by the base, right? So 2,781 divided by 10, and well, there's obviously going to be 278 in the quotient, and then there's going to be 1 left over, that 1. Okay, so that's our remainder, and that's what we put all the way in the right-hand place. Okay, so this is our next number that we use. So the actual quotient part is the next number, right? The remainder is what goes in our final solution, right? So this is our goal. So we bring down this number, 278, and again we just divide by the base and place the remainder next to it. Okay, so 278 dividing by 10 is easy, right? We see there's going to be 27 and 8 left over, so the quotient is 27, remainder 8, and we place that 8 right here to the left of our previous digit, and we just repeat this process until this number here is a 0. All right, so we pull down the quotient here, which was 27, and that's our new number, and divide by the base and place the remainder to the left. So 27 divided by 10, that's obviously going to give us 2 with 7 left over, so the remainder comes down here, and then our new number is 2. All right, divide by the base, place the remainder to the left. 2 divided by 10 is 0, and the remainder is 2, so we place the 2 there. And our number is 0, so that's how we know we're finished. Okay, and sure enough, in our goal, we see it's 2,781, right? That's the initial value we started with. But this idea can be applied to other bases. So instead of dividing by 10, right, we could divide by a different base to get a different outcome. All right, so let's try one. Let's try decimal to binary. Okay, so we have the decimal number 23. This is the value as a decimal. So we start with our number, write it down, and we have a goal. We don't necessarily know how many digits this is going to be, but we're going to divide by the base and place the remainder in the rightmost position. Right? So 23 divided by 2, that's 11, and then we have a remainder of 1, so we put the 1 here. We pull down this number, the quotient, so our new number is 11. Divide by the base and place the remainder to the left. So 11 divided by 2 is 5 with 1 left over. The 5 is our new number, and the 1 goes into our goal. Divide by the base, place the remainder to the left. Okay, so we brought down this 5, so 5 divided by 2 is going to equal 2 with 1 left over. Right, so that remainder comes down here, and then 2 is our new number. Right, so divide by the base and place the remainder to the left. So 2 divided by 2 divides evenly. It goes in one time with a remainder of nothing. So that remainder goes here. Right, our new number is 1. Divide by the base and place the remainder to the left. 1 divided by 2 is 0, but with 1 left over. So that remainder is placed there. And notice we're left, the number that we pull down now is 0. So that is our final answer. This is an algorithm, and if we use this algorithm, we know that we're finished when this number equals 0. All right. So the value of the decimal number 23 is 10111 in binary, and we can double check that, right? We know that this is the ones position, So that's 1, and then this is a 2. So 1 plus 2 is 3, and then this is a 4, so 3 plus 4 is 7. This would be an 8. We don't have any of those, so this would be a 16. So what's 7 plus the 16 in this position? Right? That's 23. So we can see it checks out. So that's how you check it. We already know how to convert binary to decimal. So if you convert decimal to binary, if you want to confirm that it's the correct answer, try to convert it back. And if you get the same answer, then you know you're right. Or else you made 2 different mistakes. Anyway, let's try one more. We're going to go decimal to hexadecimal. Okay, so remember hexadecimal is base 16, right? So numbers that are represented in hexadecimal are actually quite large in only a few number of digits, whereas binary is the opposite is true. To represent relatively small numbers, it requires a very, very large binary number, and I mean large as in the number of symbols it takes to write the number, because both the quantities that are being represented are the same, right? It's just the number of digits it takes to do it. Right? In hexadecimal, you can represent 16 numbers with just 1 digit, or in binary, it takes 4 digits to represent something in 16 different items. Right? So here's our example: 7,503. That's the value as a decimal number, and we're going to convert that to hexadecimal. Okay, so it's the same system. We start with our number, 7503. We have a goal. We have some number of digits. Divide by the base and place the remainder in the rightmost place. Right. So 7,503 divided by 16. Get your calculator out, and that's 468 with 15 left over. Well, we can't just put 15 in this base. That doesn't make sense. We have to convert that to the hexadecimal digit. That makes sense there, right? So we remember that F is 15. Okay, so we place that remainder in this position, and we have a new number. Pull that number down. Divide by the base and place the remainder to the left. All right, so 468 divided by 16. Get your calculator out. That's 29, and then a remainder of 4. The 4 comes down here, right? And so we're left with 29. 29 is our new number. Divide by the base and place the remainder to the left. So 29 divided by 16 is 1, with 13 left over. Okay, so 13 is not a valid hexadecimal digit, so we have to convert that. So we know 15 was F, right? So 1 less would be D, that would be 14, and then 1 less, 1 less would be E, and then 1 before that is D, which would be 13. So we know this value 13 is D. And if you needed to type it out, you could do that, right? Keep track of the A, B, C, D, E, and F, but eventually that should be something you memorize. All right, so D is 13, right? We still have this 1 left over. We can only stop when we have a 0 here. Okay, so that's very important. So we have 1 left over. Divide by the base and place the remainder to the left. Oops. Left that off there. All right, divide by the base, place the remainder to the left. 1 divided by 16. Well, that value is 0 with 1 left over, and we place that item here in that position. Okay, so 1D4F is the value of 7,503 as a decimal. 1D4F is the value as a hexadecimal. Okay, so that's the system you use to convert numbers to from decimal. So you start with any decimal number, and then you convert them to a particular base using this algorithm. All right. Now there's one more kind of conversion that's very useful, especially in terms of computer science. There's a special relationship between binary and hexadecimal. Okay, so binary again is 0s and 1s, and hexadecimal is base 16. So base 2 and base 16. So if we make a quick chart of binary numbers, here's the decimal value of each, and then on the right is hexadecimal. Okay, so here, how do you represent in binary the number 0? Well, you can just represent it as 0, right? But if you add zeros to the left in any Arabic system, it doesn't add anything, right? Even in decimal, right? If I add a bunch of zeros here to this 2, it's still just 2, right? So in binary, a lot of times we talk in terms of bits, and so we go ahead and explicitly write out that 0, and that's fine. So we have 4 bits here, but we increment 1, right? So this is 1 in binary, and the same in hexadecimal. And then we're out of digits, so we have to spin this back to 0, and we add a 1 to the left, right? Okay, so that's 2. We add 1, that's fine, that's 3. Now to add 1, we're out of digits, right? So we have to spin that back to 0 and then add a 1. But this one's out of digits, not 2. So we spin it back to 0 and then add a 1, right? And we keep this going. We see this pattern emerging. And as we count all the way down, we see by the time we get all the way down to 16, there are, actually the number is 15, because we started at 0. All of these 1s are taken up. If I were to add 1 more, I would have to have a new placeholder to the left. Okay? But this perfectly translates. 4 bits of binary exactly equals 1 hexadecimal character. Right? If I add 1 more digit to this hexadecimal value, it would have to spin over, and I'd have to have a 1, 0 here. Right? The next number here in hexadecimal is this. Right? To us, we're used to seeing this, and that means 10 things. Well, it only means 10 in base 10. In base 16, this is the 1s spot, and there's 0 1s, and then this is the 16 spot, and I have 1 16. So 1 0 in hexadecimal is actually 16, and then 1 1 would be 17, right? So same over here with binary. If I rolled over and had 1 more here, that would make this one roll over, that one roll over, that one roll over, and then I'd have 1 more digit, right? So the cool thing here is that binary, 4 digits of it, translates perfectly to 1 digit of hexadecimal. That allows us to translate between binary and hexadecimal very easily, especially if you have this chart in front of you. All right, so you can always, whenever in doubt, you can just make this chart real quick. You should, all of you should be able to write out the binary numbers, and there's a pattern here. Notice everything on the right-hand side alternates 0 1 0 1 0 1 0 1 0 1 all the way down, right? The next column alternates 0 0 1 1 0 0 1 1 0 0 1 1, right? The next column alternates 4 zeros, 4 1s, 4 zeros, 4 1s, and then this one is 8 zeros and then 8 1s. Okay, so that's an interesting pattern. If we added 1 more column, it would be 16 zeros, right? Because basically each one of these numbers, you could put a 0 in front of it, and it doesn't change the value. So these would all be zeros, and then we have 16 more just like it that have a 1 in front. Okay, so that's the other pattern. Another pattern you could look at, right? If I put copy to all of these and put them underneath, I would just put a 1 in front of each one of these, and it would be the continuation of the numbers, counting them out. Okay, so always be looking for patterns in numbers in mathematics and computer science, right? So 1 digit of hexadecimal is equal to 4 digits of binary. Okay, so that allows some interesting conversions. So let's take one of these numbers, 1D4F, and this is a hexadecimal number, right? The giveaway is the letter D and the F, right? So we put it in these digits, but what we can do is each one of these digits we can translate to something in our chart here. So what is a 1 in binary? A 1 is these 4 digits in binary. So a 1 in hexadecimal is equal to these 4 digits in binary. A D in hexadecimal, right? Remember that's 13, are equal to these 4 bits, 1101, 1101. And then a 4 in hexadecimal, look in our chart, is equal to 0100. So that's here, 0100. Each one of these digits is the same, right? 4 bits of binary matches to 1 bit of, or 1 digit of hexadecimal. All right, and then F, we know, is this last one, that's 15, and that maps to 1111, right? So all of these together gives us this value, and we can just strip off the leading ones because we don't need them. So that gives us 1, 1, 1, 0. That's 1, 1, 1, 0. And then we have a 1, 0, 1, 0. Right? And then we have a 100, That's the 100. And then we have 1111. And this is the value is binary. Okay, now going the other direction, let's try a different number, right? So I just randomly threw in some ones and zeros here. The trick here is we have to start sectioning it off in blocks of 4, but we have to start on the right hand side because we can add zeros to the left, right? That doesn't change the value. The really important step here is we start blocking them off from the right hand side. Okay, so here we have 1010, that's our first chunk, and then we have here 0101, that's our second chunk, and then we have 0010, third chunk, and then we have a 1. Okay, and that's fine. And we can just pad that 1 with zeros on the left because it doesn't change the value. Now we have to go look in our chart. What is 1010? Well, we look here and we find 1010. That is the number 10, which is the value A in hexadecimal. So 1010 translates to A. 0101, look in our chart. 0101 is a 5. Okay, so 0101 translates to a 5. 0010, look in our chart. We should know that one's a 2 though because it's the 2's place. Right. And then 1, this one should be obvious, that's a 1. Right? So the resulting value we've converted binary to hexadecimal very easily, 125A. So you can go back and forth between hexadecimal and binary very easily, especially as long as you draw out this chart. Right? Eventually you will probably memorize the conversions and you won't need to do that. And that should be something you work on. Right? So that's how you convert from number systems. And this all becomes very important the more you learn about binary data and computers and how data is stored and how to convert numeric data into binary data so it can actually be used on a computer. All right, so that's number systems.